welcome Maren, because Maren is going to present this design of WAAM-Steel Nodes for renewable construction. Okay, thank you. Joseph, we're going to start.
Yeah, so thank you for giving me the opportunity to speak to you. Now I will just, it's okay. And also thank you for all these great presentations, which are really interesting, and all these different kind of additive manufacturing. But I'm really happy that we now talk about steel. And I will just okay, I don't like this. Yeah, and my presentation today has a type design of WAAM-Steel Nodes for reliable construction. And I'm a PhD student at the Institute of Steel Construction and Material Mechanics at TU Darmstadt. So let me show you what you will hear in the next 50 minutes. I will start with steel nodes and what I mean with that. Of course, I will give you an introduction into wire arc additive manufacturing, which is short WAAM. But I guess Benny will also tell you more about that. So for me, it's just like really a short introduction. And then I will focus on the research aspects concerning the design, and there I will really go into the material. I will conclude everything with the next step and what I want to do then. So steel nodes. The computational engineering, or the capability of computer, allows us to build ever more spectacular buildings. And when they are really high and we have high loads and wide span, then steel is the material we choose. We have these linear components, which are really, really good for these high loads. But the problem are the nodes which connect these linear components. So because all the nodes are really individual, and this leads to high costs for construction in production. And also there's more material used than we actually would just have to use when we're just looking at the structural problems. But it's more easy to produce, and so that's why we do this. But with additive manufacturing, we can make it better. We can form like whole complex structure by just a few individual components. So we take all the complexity and shift it to the nodes. And that leads to the easy preparation and the reusability of the linear components and material efficient joining components, which are then the 3D printed steel nodes. And now I want to say how we will print these nodes from steel, and therefore I would suggest to use the wire arc additive manufacturing, or just short WAAM, or WAAM, or you want to spell it, which is actually just normal gas shielded metal arc welding. But unlike in common construction, where we use the weld to connect two pieces, we use it to create the second piece, or just the piece itself, by welding on top of each layer. So the steel wire is the printing material. And when we use the arc for energy input, then it melts, so like welding, and we can print 3D. So when we use more multi-wire feeding systems, then we can also print up to 10 kilograms in an hour. But I am now like for 2.8 kilograms in an hour, so not that fast, but maybe we can take more. So how's the process working? So yesterday when we were in the lab, it was really nice for me because it was quiet, or I here have no, not the noise, but it's really noisy. And also it's not so cool for the eyes, you can imagine. But you can really do like cool structures. That's just a star turning into another star. Okay, so when I want to design the nodes, or when we want to design and use the nodes for really construction, then it comes to research, some research aspects I want to focus on. And okay, the first thing or first question what comes into mind is what are the external conditions for these nodes? So what kind of loads are on it? How's the geometrical surrounding? And of course, when is this worth to 3D print such a node? So I don't think when we just connect two beams rectangular to each other, then maybe we won't choose a 3D printed steel node. But when we have like these complex things where the beams connect each other in from different direction with different rotation, then maybe a 3D printed node is good for that. So we have to think about the geometry and the loads, of course. And the next thing is what type of connections are usable. Because here I have just like put the beams on it and then print it like directly to it. But when we want to use it later, we need some connection points where we can apply our 3D printed node. So like here's a head plate, but this head plate isn't so good. So this normal type of head plate is, and for material reasons, maybe not the best way to do it. Because I skipped some slides, so I have to do it all on one slide. We can think about like this flange connections or back plates, and also head plates. It depends on what kind of loads we have to transfer. And the last thing, and maybe the most interesting question, is how does the printed structure behave in the end? So I'm a structural engineer. I want to calculate the structure. So that's for me the most important question. And all this comes to one question I want to answer is, how should the design process of WAAM-Steel nodes look like to assess the needed load-bearing capacity? And I now want to go more to the structural behavior of this printed steel nodes. And the first thing is then the connection means. And therefore, now I guess 3 years ago, I made like a small test series on shear connections, where I compared like the conventional steel with a bolt hole and then a bolt screw and then just tension it. And then two kinds of 3D printed steel plates, which are either like printed in the tension direction or perpendicular to it. And what we can see that all of these like look, when thinking of the failure state, they look like same. So I would suggest that it's a good behavior. And the next thing I want to do is to test the tension connection. And but I think it will work in the same way. But I think I have to do this. So. Okay, and now coming to the material. So this is like the load deformation or the stress strain curve of yeah, a WAAM plate. And now I yeah, took out some specimen, 3 in the direction of the research, well, and 3 also parallel to the printing direction. And what we can see, we have a slight anisotropy. So, but the Young's modulus is quite the same. So for the elasticity, we can say there is no influence of the printing direction, or nearly no. And the yield strength is then different to each other, and also the tensile strength, and yeah, also the elongation factor. I try to like use it for material model, and there I use the Hill's criterion, and we can see that we can calculate it quite good, at least until the tensile strength. Yeah, and the next thing is, yeah, actually, we won't use 3D printing for just printing walls. We want to have maybe more complex structure or some different kind of structure, because if we just print walls, it wouldn't be so like really, it wouldn't be good for the costs. That's why I make some tests on the intersections. So how is the printing strategy influence the material behavior? And we tested 5 strategies. So just it's an intersectional point. Here the world goes through, and here it changes everywhere. And here we had like an L, and then we printed that on, and yeah, we have here like what's the one? Huh? Yeah, we have like going around, like one of the things around, and here we have just put 3 balls right beside it. And we have to have a reference to compare it to. And yeah, what I have to say that we really looked into this slide and wanted to have it like really even and like good looking. Yeah, and so not to have like voids or so on. And yeah, that was the results. So quite interesting that the reference, which is the long line here, is yeah, it's is lesser than the intersection, and the intersections are like around the same space. Why is it? We suggest that it is because we bring more heat and more energy into the intersectional point than we had at a reference. Because here in the reference, we had just 3 welds, but here in the intersectional point, we had like 6 welds connected. Yeah, and also there are some other researchers, not concerning on, we're not focusing on intersections, but focusing on the influence of printing multiple welds per layer, and what is the influence of that. And they saw like if we have more welds in a layer, then we get a higher tensile strength. And also if we change the energy input per layer, then it's also, but this changing wasn't so high. But when I looked at my specimens, where it not really had a detailed investigation, so I actually had different kinds of investigations, but now I compare them, and then I see, okay, the highest line is for 1 one walls in a layer, and the lower lines are for three walls in a layer. So I can define that one point. So I will do more detailed investigation on 2, 3, and 4 layers, walls per layer, and maybe then I can derive like, okay, we can say like for 3 walls, or we can have the material properties for 3 walls, and then say, okay, when we have 5 walls in a layer, then maybe the material will behave like this and so on. And so I can use this to then calculate the material behavior or the structural behavior of the node in the end. So what are the consequences for the design? I didn't focus today on the form finding, but anyway, that's also what Roberto says before. You have to think of all the load cases when designing a node. Yeah, and also you have to clarify the geometry conditions. Next point was what I just shortly show is that the connection means work like with hot-rolled steel, but we should think about other possible connection types. So not just use the conventional connection types or the conventional connection type you would use for this kind of node, but think if you can change the way the connection works with the 3D printed node. Yeah, and the last thing is that the manufacturing process does influence the structural behavior. So you have to consider the printing direction and of course the slicing strategy when you want to calculate the bearing capacity. So in the end, I would suggest kind of this workflow. You have some external condition, and then you do the form finding or find a form, but you have to think about the manufacturing strategy and then maybe put some some things into your form, and then printing the structure, of course, and with the same parameters with which you printed the structure, you have also print some specimens, some reference specimens, and get the material properties. You have to monitoring the process, and then you could put everything like the manufacturing strategy, the material properties, and the monitoring like failures or so on into the simulation model. And I think, or I hope that you can calculate the load bearing capacity. And I do this before, but that wasn't so like straight on because they were different. So I hadn't applied or invented this workflow before, so I had to connect different types of investigation and put them together. But here I have installation of that and this red one was the test. And the blue lines were the measurement material, and really look also into the anisotropy. Yeah, I guess that is, my next steps. Of course, I have to evaluate the material properties for a different number of welds per layer, then do the tension connections, and finally, until this summer, I want to finalize one design where I really use the workflow I implement. Yeah. So thank you. Questions? Yeah.
Was like this already. It's okay, can't wait. It's quite, I'm not fully aware. I know the process and know from Darmstadt working on it. But do you have, I saw the numbers, you had on mechanical properties of your final printed element.
Yeah.
And I was under the impression that is in my mind, the fact that you're using Archibald process would lead to a steel product with lower quality or lower tensile strength than normal steel. But then I saw your results being the order 500 megapascal, 400. Am I wrong in my assumption, or did you bring me something else?
No, I print with the lowest type of steel wire you can find, which is the most the cheapest.
Yeah.
But I guess the suggested yield strength is 420 or so on. So that's quite in the same.
You still get 400.
Yeah.
So, okay. Then there was no assumption.
Yeah, but it depends. Maybe my parameters are good. So that's why I say you can't just say, okay, I just print, and then I found in some research paper the material properties, but you have to test it yourself.
Because my concern would be if you had a loss on the properties, then you're designing an element that's very important, with a lot of concentrated stress, with a material that has lower grade, because the process of affecting it. But when you saw the results on there, if you almost still, so keep using this for.
Yeah, I want to.
Thank you.
I won't change them.
Question to this box printer.
Yeah.
Cut out the specimens.
Yeah.
And your tensile test, did you check whether the yield, when does it yield? Does it really yield in that?
No, that's true. It doesn't yield there. So there must be more strength than in the. So it's
Actually always here just before this. And is it visible or do you have a specimen? Could you detect?
actually in that part, like in the middle, here in the middle, there were holes and voids, so you can or pores. But there it doesn't crack. Right, like here. The problem is, or after that, after doing this tensile test, just like the normal tensile test, I also did some tensile tests on some failure specimens, and there I used the DIC. And yeah, but then I thought, okay, I should use the DIC also for these specimens to see how the strength and the Young's modulus, the elasticity verteilt. Yeah.
On the previous slide, where you showed the when you usually cut out these specimens, polish the surface. Are they do they still have the printing?
No, they're drilled outside, so you just have like the inside of the structure. No. Yeah. Right.
And then perfect, because then my actual question is, do you have a hypothesis for the and like for the origin of this antitrust? Like the micromechanical reason for the anisotropic effect here.
Not yet, but I want to focus on that because there are some research about Edelstahl. I don't know, stainless steel, yes, and there is like a high anisotropy inside when you print this, and there also have some reasons for that, but I'm not sure how I can shift it to that. But yeah, but anyway, the anisotropy could be that they not connected so good, so because there's not enough energy.
And then we have this follow-up question that can you predict level of anisotropy from your printing parameters? And could you like identify the physics that lead to this effect from the studies that you don't know? About scaling norms, that's what we're talking about.
I would love to do this. I'm not sure if I can reach it. But yeah, and that's why I actually just focus on my parameters. Maybe I will do some studies on different parameters, maybe with more or less energy. But yeah, that will be like the outlook. Because now I have to focus on really these parameters because I can use them. And yeah, I don't want to change it.
On page 11.
Oh.
Okay, but it has less linear behavior.
Right.
Okay. Do you have any hypothesis why this is like this behaves like this?
But that's like always for high strength steels that, or most times that they have less elongation.
But the release process also be reason because in the reference, as I understand it, to bring 3 layers next to each other, and the other ones will bring first the edges and then bring 1 layer in between.
So there were different. Yeah, there were different strategies. So here, actually, like the other one is actually also just a tree where they start in the middle and then just put on the sides of the other 2 layers. So actually, we thought, okay, I'm so glad that we've done this reference. I thought, okay, we can just use this as a reference and then we will have this paper. Yeah, this is a really reference to just a wall, and you can see there's like really another behavior.
Thank you.
Yeah.
No, I have a quick one. Do you have an experience or something to tell about the workbench?
No.
You don't experience that? Like, because I talked to companies that are doing power manufacturing, and because of the printing, they get basically like you print on a steel plate, right?
Yeah.
Then
yeah.
high definition plate, and therefore your application requires high precision, right? If you work with steel nodes and so on. If you have an experience or you have any features about it and how you would control it?
Yeah, that's also one kind of research you have to focus. How is the printing strategy also influence this, this warpage and displacement? Until now, I don't have that much deformations yet, but I didn't. Yeah, of course, we had that also when printing the bridge. Anyway, yeah, I have to focus on that, but in summer I will print and start printing, and hopefully I have done a node which works, or maybe I have this warping problem.
Because I think the application is very important that you have that kind of
yeah, that's right. Yeah.
That was a factor.
What about the quality of
What?
Pull your element after printing, because I think it's really affecting the properties also.
I didn't understand what was the
When you cool down the
Cooling.
cooling. Yeah. Yeah, different types. But that's also one point one can investigate. How is the cooling and like the time of cooling between the layers influence the behavior, and also the type of, because we can also use, or we use air pressure, and we use also air pressure with water inside. we tested that, and the behavior was actually the same, because the weld is so cold that it just takes out the energy, and then the hydrogen is away, and you can weld on it again. Yeah, but I don't have any results yet. Air pressure. Yeah. Okay.
Thank you.